Hello all. So we will talk about gate driver, which is going to provide you galvanic isolations. So gate drivers are very much in demand for automotive applications where we have to have battery management systems, or we need to like find out some 3 kilowatt power supply or something like that. So a lot of automotive applications these days are coming which requires isolated gate drivers. So there are various gate drivers that we have already seen in various power supplies, whether it is included MOSFETs or MOSFET will be outside. However, this very simple gate driver which we will see right now, it is having isolation capability of 3750 volt RMS, and we'll try to understand the concept of gate driver with isolation using one of the IC which we have taken into account from ROHM semiconductor, and this will give us an idea of how to design gate driver designs using this particular IC, as well as extend the concept with other manufacturer ICs as well. So we'll talk about BM61M41 RFV-C. Similar to that, just replace with S, so this will be another IC. Okay, so as you can see from ROHM semiconductor, it is given that generally one more thing I'll just tell you before going into this particular isolation voltage of this much, which is 3700. Generally the demand for gate driver isolation voltage is 2 kV to 4 kVs. Okay, so it will be varying from, let us say, 2500 volt to 3750 volt based on the class of devices or class of products that you are going to design. Alright, so this is the data sheet that we are going to discuss, and what are the features and what are the different applications that is there. So already I told you these are mainly used in automotive applications for battery power management systems. Okay, so let's get into the general descriptions. As we can see already, this particular gate driver is a gate driver with an isolation voltage of 3750 volt RMS. It has a IO delay of just 65 nanosecond. This is very small, and minimum input pulse width can be as low as 60 nanoseconds. So that's the beauty. Means it can work at very high speed, it can work at very high frequency as well. It has the under voltage lockout function and Miller clamp function. So Miller clamp function will actually make sure that the remaining charges on the MOSFET, the gate driver where it is going to drive, that gets dissipated. Okay, now let's get into this some of the features that this particular IC offers, and the same way you can compare like for your other applications as well, or other ICs as well. So you must have AEC Q100 qualification. It is going to provide you galvanic isolation. It has active Miller clamping, which helps you to dissipate the extra charges during the off phase. It has under voltage lockout function, which actually saves your system from starting before the voltage reaches to a minimum threshold voltage, so that the system doesn't go in wrong position. Okay, what happens is, let us say my system is supposed to start at 12 volt and my system is starting at 9 volt itself, so there will be a requirement of under voltage lockout, so that there will not be overload burdens on the system. And the next part is, it is UL 1577 recognized as well, which is having grade 1. As you can see, very simply, this particular IC will be used to drive my MOSFET gate driver of a MOSFET, right? And key of specification we have already seen. The only one more thing that you can see is the output current capability is up to 4 amperes. So to drive the gate, let us say this is my MOSFET that we are going to drive. So the gate driving voltage and the current rating will be up to 4 amperes. Okay, the best part of this IC, why I have chosen this particular IC to make you guys get through this gate driver isolation gate driver, is because of very low pin count. So we'll introduce one more IC with a little bit higher pin count of 28 pins, but this is just 10 pin and it is going to do all the job that is needed. Okay, so if we see a typical characteristics, let's get into the typical circuit diagram. So what we see is, we have been given this particular IC. If you see physically, this is very wider version. So this is wider version because there is a isolation that is given in the middle of the IC. So this is kind of physical isolation that is given. That's the like reason it is having, it is going to give you a very good isolation voltage of 3750 volt. So as you can see, this is the isolation that is marked here. What is going to happen is, we have, let us say, side 1, and this is, let's say, side 2. So side 1 is your like input side, side 2 you can consider it as output side, which is going to drive the MOSFET. So this is the MOSFET which will be connected to your power supply and all these things, and this is how it is going to drive. Okay. Alright, so this is my drain source, and this is my gate which is going to get driven by this particular gate driver. Now let's try to understand this particular application circuit. So we have ground pin, we have supply voltage pin which will be working of 5 volt, and this is my input A and input B. So input A and input B actually works in like a PWM forge, but at the same time one of them has to be either high continuously or low continuously to make sure the gate driver is always in switching position or in switching condition, or whether it is working, right? So that we'll see when it is low or when it is high. So generally I'll tell you that you can give one PWM signal here in input A, and input B you can keep it pulled low. That is number one condition. So my input A and input B is there. Okay. So first one, what you can do is give input A as PWM and pull it low. Okay. So this is first condition. Second condition can be pull this one as high. Okay. So as high, and give PWM into this one. Okay. So PWM. So this is the second way to drive this particular gate driver. Okay. As you can see here, coming back to the output side, we'll drive it, let us say this has a capability of 9 volt to 24 volt or something like that. However, we will drive it with 15 volt voltage rating. Okay. So 15 volt we can give it to VCC2, and we have a secondary ground kind of thing it is, and we have this pin as output which is going to drive the gate. It has a Miller capacitance. So what is going to happen is, this Miller clamp will give a path for discharging the circuit. Okay. So whenever this gate goes switch off, so at that time the charges will get discharged through this particular path. Okay. So in that case what happens is, this particular MOSFET will get switched on, and this will provide a secure path for the charge to dissipate. One more thing what we have to do is, we have to give some of the bulk capacitor at the VCC input side, as well as some smoothing capacitor. At the same time we have to do the same job with the output side power supply. So hope you have now a very good understanding about what is the basic understanding of this gate driver IC. One supply, one PWM signal, with one of the other pin is pulling it low or high, and same way you are going to get your output to drive the gate. So very simple circuit. Let's get into the IC specification. So basically we have to always get into those things. So we have already told you, like, this is 10 pin device. Okay, and it is very wide device, so that it is like achieving very good isolation voltage. Okay, as you can see, we have GND2 is output side ground pin. So GND2 is output side ground pin. We have MC pin, which is Miller clamp pin. Coming back to this output pin, which is going to drive the gate of your MOSFET or IGBT. We have VCC2 pin, which is going to have output power supply pin. Okay, so output side power supply pin will be required. Then we have GND2 again, one more, two grounds are there, one more ground is there. Okay, and two grounds are primary side also, like side 1, which is input side. So we have input side 2 grounds, and then we have input side 1 power supply pin, which will be taking let us say 5 volt supply. Actually it will take 4.5 volt to 5.5 volt, but I'll suggest you to keep always 5 volt. Okay, and there are two control input pin, which is my input A and input B. So basically the beauty of these two pins is they can work as a enable and disable pin also. Okay, so whether the PWM pin is available or not in one of the pin, if other pin is pulled other way, like high, then it will not be working. So I'll tell you how does it work. Okay, alright, we have already discussed about VCC1, we have discussed about ground pin, we have discussed about VCC2 pin. You have to bypass with capacitor. Okay, between VCC2 to ground pin, same way VCC1 to ground 1 we have to bypass with capacitor. Okay, coming back to the input A and input B pin, what happens is we have to determine the logic. So our aim is to get high at the output pin. So we are going to have this output pin, and this is my gate of the MOSFET, which is going to be driven. So this is my drain, this is my source, and this is the place where we are going to drive this through my output signal, right? So what is happening is my input is low, then only it will be high. As you can see, all the times it is low whenever it is high. Okay, so if you want to disable the IC, you can simply pull your input pin B as high. Okay, or if you want to work with input A, we'll first talk about input B. Okay, so what happens is if you pull it low, then what is going to happen? If input A is low, then it will be low. If input B is high, input A is high, then it is going to be high. So basically, you pull your input pin low and then give a PWM signal at the input A, so that you can get your low high at the output. That is one condition. Okay. Another condition can be you can keep your input A as high, because input A, if it is pulled low, then both the condition it is always low, and if it is pulled high, then you can see the low high is there and low is there. So what will happen is, if you put input A at high, then you can give PWM signal to input B. So both the ways you can utilize. So I'll suggest you to keep only one method. Okay, we have output pin and we have Miller clamp pin. So Miller clamp pin, actually what is going to do, as I already told you, that the MC pin is for preventing the increase in gate voltage due to Miller current of the power device connected to the output pin. So there will be, like increase in gate voltage. What happens is, this particular gate voltage will increase. Okay, so in that case what happens is, this particular Miller clamp function is not used, then you have to sort it. Okay, anyway, this we will be using, so we'll try to utilize this particular Miller clamp pin functionality as well, and you can avoid your gate voltage increment because of switching off conditions. So how does it work? Basically, this Miller clamp voltage is whenever this particular, let us say this is my drain, this is my gate, and this is my source. This is my source. So what is going to happen? This will provide a path like this. Okay, to get the charge grounded. Okay, that's the beauty of this particular Miller clamp. If you do not want to have this kind of functionalities, then what you can do is, you can directly ground it. Okay, so you don't use this particular functionality. That will be little simpler design, but I'll suggest you to keep it connected to the gate of the external MOSFET that we are going to drive. Now let's talk about the control functionalities. So what is going to happen? So let us say we have input A, we have input B. Okay, now what we are going to do is, we will see whenever input B is low, then only it will work. Okay, that's the beauty. Now we'll try to understand what is happening. As soon as my input A goes high, so it will take a little bit of like a delay time, which is going to have TP on time. Okay, TP on time. So this TP on time, it will take, and it will take little time, which is going to take, let's say 10% time to 90% time, which will be considered as T rise time. Okay, so T rise time, and this is how it is like working. So as you can see, input A is high all the time and it is working. But let's say if you want to switch it off, then what will happen? If you pull this input B to high, immediately it will switch off. Okay, so this is what is happening. As soon as I pulled it high, my input B, it is going to take a propagation delay of off time, and after that it starts falling down. So you can see there is a fall time which is going to have T fall. So T rise is there and T fall is there. Okay, and you can see till the time it is pulled up, it will always be low. Now since the input A is always high, I have made it, so as soon as if we pull it low, again it will become high. So this is how it is working. Got it? So input B is low, means it is working whenever my input A goes high. Input A goes high, and if input A goes like low, then it will not be working. You can see it will not be working. Even if input B is low, it will not be working, it will go low. Okay, Now let's talk about the driving of the MOSFET by this particular IC. So what happens is very simple design. If you want to do, you just have to give one capacitor, like we will provide two capacitors here, let's say 0.1 microfarad capacitor and let's say 22 microfarad capacitors with 5 volt input at VCC1. Okay. Now coming back to the input A and input B, so we have, let us say, PWM signal here, and we have here let's say pull it low. So pull it low. So this is how it will be working in working condition. Coming back to VCC2 side, so we give 15 volt, you give one let's say 47 microfarad capacitor with let's say 0.1 microfarad one more capacitor, and this is my gate. Okay, so gate, this is my MOSFET that we are going to drive. So drain, gate and source. Okay, so this drain will be start getting short together to this source, like start getting switching on or switching off this particular MOSFET due to this output signal which is going to come due to this PWM signal. Okay, and this Miller clamp pin can be directly connected to the gate of the MOSFET which we are going to drive, and this particular ground will be sorted to the ground of our source of MOSFET. Okay, so this is one way of driving. Another way of driving is with a buffer circuit. So this is my buffer circuit that we are having, and same way you can change your PWM signal, input voltage, output voltage, all these things we can supply the same way what we did here. The only change that we are going to have here is we have here push pull configuration or totem pole configuration. You can see push pull configuration of two transistors in like N type like NPN transistor and PNP transistor. You can design this thing using MOSFETs as well and send this through a driver circuit to the gate of our MOSFET. So this is the beauty of driving silicon MOSFET with buffer circuit. Okay, so this will be much more useful, much more helpful, but it will increase the cost of the system while you are designing. However, this is suggested. Good, so this was all about the gate driver circuit that we have just now studied. And now actually this particular IC is coming up with lot of evaluation kit and all those details and design and details from ROHM Semiconductor. So we'll just let's get into a little bit of look into that particular understanding. So as you can see, we have evaluation kit. So I'll paste this particular link also in the link window, in the description window, so that you can have a look on later on. So this is a gate driver which is having a evaluation kit of BM61M41 RFV-C. So same thing we have studied just now, and this is also called as EVK001. There is one more EVK002. You can have a look on that also. Now if you look into the board, so board is looking like this. We have top side view which is coming up with the port pin of like input A, input B, and we have VCC1 and we have ground. So this is my side 1. Okay, and these 4 port pins can be taken out to the microcontroller pins, microcontroller board. Okay, like control card board, my MCU board we can take out. So this will be kind of a control card board, and we will be having side 2. So this is how it is connected, like we have VCC power and we have ground and we have gate of the MOSFET that we will be driving, which will be connected outside the board. Understood? That's all. So this is what it looks like from top side. From bottom side we have like you can see we have supply capacitor. 2 provisions are given which is having C21 and C22, and similar to that 2 more capacitors are the input of supply input of the side 2. So that's all. Very simple circuit. You can see we have input A and input B which can be connected to my input A, input B. So terminal 1, 2, 3, 4. So 4 terminals are taken out into the board, you can see. And similar to that we have supply bulk capacitor and smoothing capacitor. I suppose like I can give you an advice that you can increase this particular value to, let us say, 22 microfarad minimum, plus put one more 0.1 microfarad, and for your design if you are doing you can give one more capacitor of 22 microfarad. So let's say keep 22 microfarad capacitors and 0.1 microfarad capacitor. You can keep this as a provision. Okay, coming back to these 2 capacitors, you can always keep them as let's say 0.1 microfarad capacitance. Now let us talk about output side. So in output side, if you see, we have a 10 microfarad put here, and one more provision is given. So what we can do is we can keep it, let us say, 47 microfarad capacitors. If you want, you can give it electrolytic capacitors as well, with a little bit higher values of, let's say, 100 microfarad capacitance plus 0.1 microfarad capacitance, one provision. Or otherwise, if you are using ceramic capacitor, keep it 47 plus one more 22 and one more 0.1 microfarad capacitor. That will be good idea. Okay, so what I told you is 47 plus 22 plus 0.1 microfarad, that is method number 1. Method number 2 will be 100 microfarad electrolytic plus 0.1 microfarad ceramic. So that will be my number 2. So whichever way you want, you can do that. And this is the gate that it is going to drive. This is my 0.1 ohm resistor, which is acting as like a current sense resistor or something like that, but it doesn't matter. And this is kind of RCD snubber also, like I mean, like RD snubber. So it will dissipate heat or something like that. It will give no ringing at the gate of the output, so that there will not be intermittent effects. And this is the MC pin that is connected directly to the gate. So this was all about this particular circuit. If you want to have part number, so part number listing also they have given, you can have a look on this, but I don't suggest this one anyway. I mean, we can always have a look on that. The Schottky diode that they have taken is 30 volt 5 ampere rating, so it gives you an understanding like what is the rating that you should take up for the diode selection. Okay, and since the resistors are should be like very high resistors, so in that case you have to have little bit higher power capacity. So that's the reason they have taken very big package, which is 3216 package. If you talk about all the reference designs, so this particular kit is there, which is having a very good reference design for integrated battery charging algorithm for 2.5 kilowatt LLC DC-DC converter. Okay, so this DC-DC converter is having very good reference design. So this is the link that is there. I will paste this link also in our workshop videos. And at the same time, this is having particular block diagram, and this is having schematic, and this is having part list. So let me just give you a quick look into this. Before that, I'll just give you features about this particular board that they have designed. So this particular board is coming up with constant current operation, then it is going to have constant voltage operation as well. So basically it is going to charge a 48 volt battery. Okay, so very high voltage very high voltage capacity battery, it is going to charge for our automotive application. Now it has the functionalities of like output voltage protection, output overcurrent protection, we have reverse battery protection, we have CAN communication. Okay, so CAN communication is also there, and RS-232 communication is also there. As along with that, we have LCD interface also. Okay, so that's the beauty of this particular reference design that is offered by ROHM Semiconductor. Now let's get into the online page that we have. So this is a particular data sheet that we just now talked about. So we have already covered this particular data sheet, all the design details and like particular information that we needed to design this particular gate driver circuit. So hope you have now a very good understanding about what are the things that we need to take care while designing a circuit with gate driver ICs. Alright, so we have seen all characteristics and all, you can have a look, but that was not needed, so I'm just skipping them. However, this particular application example we have already seen, and there are like recommendation that is given. Like you can see, we have two transistors Q1 and Q2. So you can see Q1 they have given a provision of this particular NPN transistor. It is having, I think, 2 amperes rating, and this is also having PNP transistor, so this will be also having around 2 amperes rating or something. So that you have to have a this thing in mind. This is diode which is having, let's say, 3 ampere rating or 5 ampere rating you can keep. So that's the meaning. Similar to that, other things we have already seen. Now let's get into the idea of other parts that we have to have. So as I already told you that we have the evaluation kit. So evaluation kit is coming into a board which is coming back to this place. Let me just give you an understanding. Okay, we saw just now that if my input is low, input B is low, then it is working. So this is working here. You can see my input A can be controlled as PWM, and it will be going high or low the gate output. So as you can see here, the graph also it's shown, like whenever my input is pulled low and my input is A is going high, so what is happening? Is going high, and as soon as, even if it is high, it doesn't matter because my input B has gone high, so that's the reason it has gone low. Understood? So that's the understanding that we should have the switching characteristics, and this was the evaluation board that I was talking to you just now. So you have a good understanding about this. So if you do have any questions, you can always ask, and you can always get proper answers about it. And this particular evaluation board is actually in 4-layer board, so you can have a look on this. Like we have top layer, we have bottom layer, we have a second layer, and third layer is there. So yeah, you can see here a second layer is there, and then third layer is there, and bottom layer is there, and top layer. So we have 4-layer board. Alright, now as I told you, like I was going to tell you about the particular evaluation reference. So this reference I will be pasting in the in the link window. So this particular reference design can give you a very good understanding, and this is the block diagram that they have shown. Sorry, this is the part list that they have given for complete circuit design that you may not be able to look into right now. We'll just see first block diagram. So as you can see, we have all the four phase driver of this particular MOSFET. So this is the 4 phase is there. Then this is going to be the high voltage battery which is going to get charging. Okay, so this is what we have. So system block diagram, it has like 380 volt typical, which is coming from, let us say, AC DC converter, and this AC DC converter is going to give you charge your battery to 48 volt. And all the other peripherals are there which is going to have this microcontroller interface, and then it is going to go to your main interface of the system. If you can see, we have gate drivers for this particular 4 MOSFETs, like 1 2 3 4. So all the 4 MOSFET that is there, it is working in complete full bridge MOSFETs. So these full bridge MOSFETs is going to get driven by my BM61M41 RFV, which just now we studied. Okay, and these MOSFETs are being driven by the PWM coming from the microcontroller. So basically, to drive these 4 MOSFET, we will be needing 4 of these our gate driver ICs, and in that case we can work with 8 PWM signal or 4 PWM signal plus 4 IO lines. Understood? 4 PWM signal, 4 PWM signal we will be working, and 4 IO lines will be required, because input B can always be pulled low all the time, so that input A only can control this particular gate driver to drive these particular MOSFETs. Okay, so this is the complete circuit that I will be explaining you maybe in the next session that we will take up. So as you can see, we have 4 MOSFETs, and the same 4 MOSFET is going to get driven by this circuit which I was just telling you. This is the gate driver IC that we are going to design. Okay, so you can see, very easy. We have the power supply to the input side with one 10 microfarad capacitor. Similar to that, we have one PWM and one control pin which is INB, like input B. And similar to that, we have output side which is having 15 volt supply with one diode protection, and at the same time we have output pin which is going to get connected to the MOSFET of the 4 MOSFET that you just now saw. Alright guys, so this was all about this particular gate driver section that we have just now studied, and if you do have any questions regarding this particular gate driver IC and how to have this particular understanding of this, let me just show it to you. So how to design this particular isolation gate driver, and why do we need isolation? Because there is a possibility that we if we go ahead with like transformer design or something like that, it becomes very bulky. So this those problems are solved very easily by these ICs designs and having inbuilt gate drivers as well. Alright, so if you do have any questions or any queries, you can go ahead and start asking one by one. We will provide you some 15 minutes of time with any of the functional based questions or maybe design related questions that you have. You can always look into it and put on your queries. Thanks a lot.